You've just finished reading page 88. I'm going to see if I can help clarify some of the ideas there. The bottom of the first page of your notes, I have a circle down here, and I think on your page the tangent line at P is drawn in, but I don't think that it came out in your copy. So sketch in your tangent line at P. So you probably remember from geometry that the tangent to a circle at a point is the line segment that touches the circle just at that one point and doesn't touch the circle again. You might remember, but maybe you talked about it a little less, that a segment that intersects the circle twice, I couldn't draw those dots, is called the secant. So what we've been doing, when you found rate of change, the average rate of change of for example, the fruit fly problem, you had 2 points on the line and you found the slope of the line between them. That line that contains 2 points on a function, we call a secant line. Just like this line has 2 points on the circle, we call it the secant to the circle. So look at this page in your book. I'm on page 88 in your book. I want to look at this picture right here. Now, secant line is easy enough to explain. Find any 2 points on the curve and connect them. That's a secant to the curve, but it takes 2 points. Tangent line is harder to describe, especially until you know more calculus. But I want you to imagine you graph this on your calculator. Let's say you knew the formula for the curve and you knew a formula for the tangent line. And if you zoomed in with that big blue point, if you zoomed in with that as the center, and you zoomed in further and further, what would happen eventually? If this is the tangent line and you zoomed in more and more, then if you got zoomed in far enough, it would seem like the tangent line, which is in pink, and the function, which is blue, and you'd only see a little part of it, they would appear to overlap completely. The tangent line is the one line in the whole universe that best approximates your function if you zoom in really far. Now I want to look at the picture at the bottom of page 89. There's a copy of a similar picture in your notes, so if you have trouble reading this in the video, you can read the notation off your notes paper. So what would happen if I wanted to find the slope of the tangent line? I know how to find the slope of the secant line. If I have any 2 points on a function, I can use the average rate of change. I can compute average rate of change. I'm going to zoom in here. So right now, you see the point P and Q are marked in on this picture and also on the picture in your paper. Right now, there's a place for you to write an expression that would give the slope of that secant line, the slope of PQ. And then you can start the video again. That expression you just wrote, you can see it's the same as the expression down here. It's called a difference quotient for F at A. And that's because it's the quotient of two differences, a quotient of two subtraction problems. And you can think about, what if I wanted, instead of the slope of a secant line, which requires 2 points on the curve, what if I wanted the slope of the tangent? How can I find the slope of the line, just write it exactly, point P? Well, we have the same problem we had when we tried to compute instantaneous speed. We can let Q get closer and closer and closer and closer to P until essentially the distance between Q and P is 0. Now you can see why we spend so much time working on limits, trying to solve the 0 over 0 problem, because that's exactly what we're going to do next. 2 quick notes before we move on to use difference quotients to find the slope of a tangent line. Because the subtraction, the difference in the difference quotients, frequently you're going to find that you're going to need to distribute a subtraction. The most common math error made by calculus students is not distributing the subtraction in a difference quotient. So if I asked you to find the difference of 20 and 3x plus 20, you would have to subtract 20 minus, and then the 3x plus 20 needs grouping symbols, and the subtraction needs to get distributed. And then one more, we're going to work very frequently with polynomial functions. Remember, to raise a polynomial to an exponent, you're going to have to put that whole polynomial in parentheses with an exponent. That means repeated multiplication. So an example here, if I had 4 minus x squared, you're you're going to have to write 4 minus x times 4 minus x. That takes 4 multiplications to simplify it. You might have learned FOIL, so if FOIL is what you think of, whatever you have to do, just notice to multiply a binomial by a binomial takes 4 multiplications.